Hi, welcome back to my friend Permu's Patio. This is the third part in our series on permutations and combinations. The first two parts talked about basics and then what permutations and combinations are. For these examples, we'll be talking about an elected committee, where the order does matter, a randomly selected committee of people, where the order does not, and how many possible hands there are of 5 cards when you're playing cards. And we'll let you figure out whether order matters there or not. So number 1, I have an elected committee of 5 possible people, and there are only 3 positions: president, vice president, and secretary. So whenever we're trying to do these problems, the first thing we have to ask ourselves is it a permutation or is it a combination? And the answer to that depends on whether the order matters. So these 5 people, we've only used the first letters of their name. If I have A, B, C and C, B, A, those are the same 3 people, but these are different committees because here the president is A and here the president is C. So order does matter. So why don't you pause for a second and see if you can decide whether you think this is a permutation or a combination. Well, because the order does matter, this is a permutation. So let's take a look at the places that are possible on the committee. How many do I have? I'm only picking 3 out of 5. Well, for the first, I could have 5 people, up to 1 of 5 people elected in that position. But once I've done that, now there's only 4 left for the vice president. And so I have 4 possibilities there. And for the secretary, since I've already elected 2 people, I have 3 there. So similar to our flower pot example, the number of possible committees where we do care who's president, vice president, and secretary is 60. Okay, and we're going to do this without formulas because, in my opinion, understanding it is more important than the formula. You can memorize the formula later if you want. The key idea here is I have 3 slots, and I'm just figuring how many possibilities are there for each. Now, let's talk about committee number 2, where I have 5 people volunteer, and we just randomly select people, so it doesn't matter. A, B, C, C, B, A. If you remember from last time, these are the same because the order doesn't matter. A, B, C, C, B, A. And see if you can remember how many possible combinations there are of 3, or how many possible arrangements of 3 that are identical. If you thought about it, if you remember, it's 3 times 2 times 1, which is 3 factorial, and that's 6. So 6 of these arrangements of A, B, and C, of any 3 I want to pick, are identical. So we're going to do this in very much the same way. I still have 3 positions open, 5 for the first, 4 for the second, and 3 for the third. But this time, for any 3 that I pick, there are 6 that are identical. So we need to divide this by 3 times 2 times 1, 3 factorial. And I would encourage you to do it this way instead of using 6, because what you'll see is many times these numbers divide out. 2 goes into 4 twice, 5 times 2 is 10. So there are 10 possible committees that are randomly selected. Different committees that have been randomly selected. Number 3, this is cards. And I'd like to know how many different arrangements of cards are there if I'm dealt 5 cards. And why do I care about this? Well, if I'm trying to figure what the chances are of certain things happening, I'll want to look at the number of desired outcomes divided by the total number of outcomes. So what's the total number of hands that I could pick? Well, as you probably know, there are 52 cards in every card deck. And I'd like to think about all these card games you played. Hopefully everybody's played a card game. And when you get the cards in your hand, it really doesn't matter whether you get 1, 2, 3, 4, 5 or 1, 3, 4, 2, 5. It's the same hand. So if the order doesn't matter, then is this a permutation or a combination? Why don't you take a moment to think about that? Well, because the order doesn't matter, this is going to be a combination. So I'm going to need to divide by the number of identical hands. And how many of those are there? Well, up here when we had 3 flowers, or 3 people, it was 3 times 2 times 1. It was 3 factorial. It was the number of people I was choosing factorial. So this time it's going to be the number of cards that I'm being dealt factorial. So in the end, I'm going to be dividing by 5 factorial. So let's take a look at what this comes out to. In fact, if you want to, why don't you take a moment right now and see if you can figure out how many different hands there are when you have 52 cards. Okay, let's take a look. I have 5 slots, 5 spots in my hand. And for the first one, I have 52 possible cards. Once I've been dealt 1 card, I have 1 less to choose from the next one. And then so on, 1 less again, 1 less again, and 1 less again. Okay? Now, I'm going to take all of this, because these are my 5, my 52 when I'm choosing 5, and I'm going to divide that by 5 times 4 times 3 times 2 times 1, which is 5 factorial. And this is just the number of arrangements of the cards that are identical, even though they have a different order. And now I hope you'll see why I said it. I think it's better to do it this way than to do it this way. 2 goes into 48 24 times. 3 goes into 51 17 times. Now, if you watched our series on short division, you'll know how to figure that out. 3 goes into 5 once, with 2 left over. 3 goes into 21 7 times. 4 goes into 52 13 times. 5 goes into 50 10 times. So if I don't have a calculator, this will be a lot easier. With a calculator, of course, you could do the whole thing. And let's see what happens. All of my numbers on the bottom are gone. So I'm going to multiply 13 times 17 times 10 times 49 times 24. And if you're using a calculator, why don't you go ahead and take a second and figure out what that number is. Okay, the number is 2,598,960 different card hands. And that's a lot. Now, we'd be remiss if we didn't do some of this formally. So what did we do here in the case of our permutations? Well, this was the number of permutations of 5 people when I choose 3. So this is 5 5 factorial over 5 minus 3 factorial. Does that make sense? What does this leave us with? 5 minus 3 factorial. That means I'm going to be knocking off 2 times 1, which is exactly what I did here. Now, let's look at the combination example. This time, once again, I have 5 factorial. Let's take a moment to rewrite this. I'm going to be number of combinations of 5 items when I'm choosing 3 is 5 factorial. It's identical to this, right? But I'm going to be dividing by the number of identical permutations. So 5 minus 3 factorial. And then the number of identicals, 3 factorial. And as you look at this, I hope you'll see why I encourage you to try to understand what's happening as opposed to trying to apply these formulas. I think if you'll practice this way for a while and get to where you understand what's happening, all of this will make sense to you anyway. The last one down here, this is a combination problem, and if you can look on Wikipedia for the chances of certain hands coming up, and you'll find that most of them are a combination problem. So this is a combination problem when I have 52 cards and I'm picking 5. So this is 52 factorial divided by 52 minus 5 factorial. And remember, all that does is recognize that I'm not counting any of these others over here. From 47 on down, they're all gone because I can only pick 5 cards, right? That's all this says right here is I have 52, and I'm going to take away I'm going to divide out all the numbers for the cards that I'm not allowed to pick. And then my last item to consider is how many of these are identical? Well, just like here it was 3 factorial and here it was 5 factorial. I just need to divide by 5 factorial. So when you look at this, the permutations are the easiest problem to do. The combinations are just the permutations divided by the number of arrangements that are identical. That's all it is. And that works whether it's 5 items choosing 3 or 52 items choosing 5. And so if you'll think first off on all these problems, is it a permutation? Is it a combination? And if you want help with that, write down what could go in your slot and see if it makes sense, see if it makes any difference whether you arrange those for the problem or not. In this one, it made a difference because I had president, vice president, and secretary. Those are 3 different positions. In this one, it did not because I was just picking people randomly, and however I arranged them, it was the same committee. In this one, again, doesn't matter because I can move the cards around, and so the order doesn't matter. And I hope that will help you thinking about permutations and combinations. It's a topic that many students get confused about, but I really do believe that if you'll think about it at this fundamental level, at this level of understanding, and not try to use the formulas right away. And I'm not saying the formulas aren't important because as you progress in math, this symbolic language of math will be very important and you need to understand it. But to begin with, being able to work these problems out really just depends on you understanding these very simple relationships. I hope that's helped with permutations and combinations. I hope you'll come back and visit us at Permu's Patio. There are other topics we talk about. And in every case, we're going to do our best to lay the groundwork before the final topic and make sure that all of the fundamental core ideas are explained for you. Bye-bye.